the self-service breaks, get a new SIM card, doesn't get fixed. Happens like, I don't know how this happened. Here's a new phone. This is some consistent issue. Another thing you know, like if some people like watch it on, they brand new.
Sure.
My neighbor has that. You know that thing? I think I have it.
Then they're all late.
No, it's really
That's what I know. Oh yeah, you're right. You're right. I didn't. Now that I'm thinking back on it, I didn't. I changed it everywhere that mattered, which is everywhere except Blackboard. Okay. Yes. Yeah.
Electric people. You thought that was going to give you some results?
No, you won't need to take the absolute value because essentially because it should be x squared, y squared, z squared, and so you get rid of any negative that's in there. And not only that, but you should only be taking that should be 1, the magnitude of the denominator. If the phone is functioning correctly, it's 1 g down, right? 1 gravitational pull. Oh, that's right. Yeah. Yeah. Okay, so welcome to 53, 23, 73, 23, Lecture 12. Today we are going to talk about computer vision. Okay, so course logistics. A2 grades will be up today. I have basically 1.5 more teams to grade, which I will do this evening. I think everybody has done fairly well, actually, thus far with the assignment. A3 is due at 6 p.m. today, more or less. If you turn it in a little after 6 p.m., I'm not going to dock you for that because Blackboard is telling everyone that turns it in that it's late anyway because I forgot to update the due date for it. So I will stick around here until 6 p.m. if people want to demo their app to me. Or you can send me videos as before, but I'd really like to be able to see it, just kind of play around with it. A4 is going to be due Friday after spring break, right? So you have this week, you have the week of spring break, and then the week after spring break, you have that whole week, and then A4 is due Friday, okay? So A4 has a module A and a module B to it, okay? So essentially module A, I want you to create an iOS application. I want you to read and display images from the camera in real time, which we've already done. And then I want you to highlight all of the faces in a scene that's coming in on the video. Somehow highlight all of the faces that are in a scene. I'm probably only going to test it with my face, but I may take other people and just put them in the scene as well, and we'll all just get there. Right? So there's a possibility of more than one face being present in this streaming video. I then want you to tell me where the eye and mouth are on the face. And if you want to do any of the highlights on this, you can use different filtering commands. Okay, so last time we looked at core image filtering, CI filters. There's compositing filters, there's distortion filters, there's all sorts of things that you can do and base them around where the eye and mouth position are and where the face position is. For extra credit, up to 1/4 point, display if the user is smiling, whether or not, and display if the user is blinking their eyes, and if it's the left eye or the right eye that they're blinking. Okay, that's module A. And it's a lot more simple than you guys think by just looking at it. Okay, essentially I'm asking you to use the iOS API that exists for doing all of this. Okay. We're going to talk about what each of these are and how to use that API and give you a little bit of intuition about what it's doing so we're not so hand-wavy. But that's Module A. Module B, by the way, I'm going to ask you to write essentially a health application. And this health application, I want you to use a video of the user putting their finger over the camera, like this, and I want you to tell me their heart rate based on that. So essentially, you'll put the flash on, they'll put their finger over the video, and you're going to look at fluctuations that are happening on the incoming video screen to tell me what the heart rate of that individual is. And that will be module B. Okay? And this is going to be a coarse estimate of someone's heart rate. Okay? I'm not going to sit there and count, oh, you're off by 2 beats per minute. I'm not going to count you off for that. That's a really good indicator. I like that. But if I'm running and I sit down and use your app really quickly, it better be higher than 100 BPM. Well, hopefully, unless I'm dead. Okay? Fair enough. And then optional, but not extra credit, probably something you'll want to do for debugging, is display the PPG signal, which is, we'll talk about what that is today. It's a photoplethysmography, which is just a giant word for your heart rate. Essentially, blood pressure as it goes up and down. Okay? So today, what we're going to talk about, we're going to talk about video processing a little bit more because we did it at the very end last time, the Look and Live application. And then we're going to go straight into computer vision. The first thing we're going to talk about is face detection using the iOS APIs. And then we're going to talk about using OpenCV in iOS. We're going to get into a lot of things that are in OpenCV that you're not going to need for this assignment. But we're going to talk about them anyway because I think they're fun, I think they're interesting, and video is probably the most common thing that you will use as a sensor on a mobile phone, depending on the applications that you're building. And a lot of people have come to me with different ideas for applications that would require use of OpenCV. Right? So we're going to get into a little more detail with some of the computer vision and things that are there. Okay, so just as a reminder, let's go over here. This is our Look and Live application, which we wrote, which essentially what we did was we created an instance of this class, which was video analgesic, which had we called it the video manager. And essentially what we did was we created a filter, and then I called a method called set the processing block for the video manager. And what I got was an instance of a camera image, which I filtered, and then returned that image for display to the screen. Right? And we used a CI sepia tone filter right here. Okay? And so essentially that was pretty easy. Whenever we appeared, I went ahead and started the video manager if we weren't running. And then in view did disappear if we are running, I went ahead and stopped it. All right? Good. So if we were to look at what that looks like, let's go to Eric's phone. I could go ahead and just show this. There I am with a sepia tone filter. Okay? Perfect. The next thing I want to talk about is updating those filter parameters on the fly. And we're going to do that really, really quickly. Essentially, what we're going to do is create this thing called a CI pinch distortion, which essentially takes the image and pulls it in to one center radius. So what it needs right here is an input radius. So how many pixels from the center am I going to go out such that I start pulling them almost like they're going into a black hole. Right? That's essentially the effect that I'm getting here. I'm going to need to tell it what the center is, and I'm going to need to tell it what the scale is. How much am I going to pull it down? So it's essentially the depth at which I'm pulling it down here. Because you could imagine just pinching something a little bit versus really, really pulling it. Right? Into the photo. Right? So I can set up a CI filter and set all the default parameters the way that I want them. So I'll say radius here equals 100, and then I'll say that the center of this is a CI vector, core image vector, where x is equal to my height, so self.view.bounds.size.height, divided by 2, because I want it to be right in the middle. And then I'm also going to subtract off the radius. And then in my y direction, I'm going to say self.view.bounds.size.width, divided by 2, and I'm going to subtract off half the radius. Okay? Right, so I get my x and y parameters for where my center is going to be. I don't know why that they call it that. Essentially, center is the top left corner of your pinch distortion. Okay, so when I apply this, I'm going to get a copy of weak self so I don't get any retain cycles. And then in my process block, the only thing that I'm going to do is I'm going to update the center right here. And then I'm going to say that the input value to this filter is a camera image. Oops. Come on. And then return the camera image. Good? Happy. Okay. So essentially what I'm going to do right now is I'm going to update the value of the center of my distortion from the user interface. And I'm going to create this thing called a pan gesture recognizer. And every time that so what is a pan gesture? Somebody tell me. Anybody? It's when you're panning across the screen. It's just a click and a drag. Okay? Like if it was a mouse, it'd be a click and a drag. When we're talking about a touch API, I'm just touching and sliding across. That's a panning. I'm panning across image. So every time that I have a gesture recognizer on a view, I can attach a gesture recognizer to a view. And I can say every time that this pan occurs, I want to know all of the information about that entire pan. I want to know the velocity that someone's moving. I want to know where it is exactly on the screen. You can get all of this information from their gesture recognition. And essentially what I'm going to do here is I'm going to create a CG point. So I'm just going to get a point, which has an X and a Y value. And I'm going to say, okay, so here's my pan gesture recognized, and it gets sent in by a user interface pan gesture recognizer, which means that I can call this location in view on that sender that gets passed in on my UI, my pan gesture recognizer. And essentially what I'm going to do here is I'm going to take this core image vector and I'm going to say point.x and point.y right down here and set those to be the center of my pinch distortion, right? So as I click and drag across, that pinch distortion is going to move on the video as I'm panning across, and it's going to follow my finger where it is, right? So one of the things that you'll notice on here is that this Y value that I get, I'm taking the height and I'm subtracting off my point.y. And the reason for that is because it's mirrored. The view is actually mirrored, and that's part of the video analgesic API, so I wrote that in there. Okay, if you guys have trouble with video analgesic, let me know. I wrote that. Okay? Okay, so we're going to set up where the user drags. We're going to get their drag location from the sender, and we're going to update our center. Okay, so let's do that in our Lookin' Live distortion demo. Okay, so the first thing I want to do here is set this up as a pinch distortion, right? So this was a CI pinch distortion, right? And if we go back over here, let's see all of the parameters that we wanted this thing to look at. Well, the first thing I did with here was I set up a CI vector, and I have this thing called self.center, which is going to be a CI vector property. So let's create that. Okay, so at property, we'll make it strong and non-atomic, right? And it's going to be of type CI vector, and we'll just call it center. All right, so it exists now, and I can actually put it in here if I wanted to, right? So the first thing that we'll do here in view.did.load is we'll say self.center is equal to, and we'll make it a CI vector, right? And I'm going to say vector with X and Y. And then we'll put in the X and the Y values that we want right here. Okay?
You need to make it self, not select.
Yes, I do. You don't have to ask that in the form of a question next time. You can just tell me, hey, you did that wrong. Okay, so this one I did height over 2 minus the radius over 2. All right, so let's go ahead and choose a radius right here. Float, radius. What should the radius be? I made it 100 before. This is 100 points, right? So it's kind of like this on the iPhone, real sized. It's a pretty big distortion. We can go ahead and, let's make it 100. That's fine. We'll call it that. All right, so now if I go to my self.view.bounds.size, dot, is it height or width? Height. Height. Minus radius over 2. Voila. All right. So we'll divide each of those by 2. Very good. Okay, and then the width plus the radius over 2. Right, so self dot view dot bounds dot size dot width over 2 plus the radius over 2. Okay, so now I can go in here in this filter with name, and inside here, I'll just call the same thing, which is filter. We want to set the value, and the value is going to be our self.center, right that. And then for the key, I'm a little dyslexic today, wow. Okay. I often do that, I think. So, all right, so that's going to be the input center that we're updating. Input center. Okay, so this is going to work. I've got an error. I've got a warning. Capturing self strongly in this block is likely to lead to a retain cycle. Okay. So let's create a weak self. Right? So, weak type of self. That's just a declaration. That's just inserting what the name of self is right here. Type of self. All right? Yeah.
So, weak self prevents you from getting the retain cycle thing. Is there a downside to always using weak self?
So not really. And the reason that there's not a downside, well, you mean like everywhere in your application?
Yeah.
So as long as your view exists, self is going to have a strong pointer to it, right? So if you're using weak pointers with self, that's fine, because anytime your code gets called, self is going to have a strong pointer to it, right? You just don't want to create additional pointers to it that are going to exist whenever the life cycle of that view controller goes to out of scope, right? And so because we're creating a block, we don't know where that block is going to be, where it's going to exist in any of the application. We want to use weak self right here. Just so that automatic reference counting doesn't always have a reference to self right there, even when the model in the view controller doesn't exist, right? So anywhere that you can use weak self, for the most part, it's okay to use it. It's probably not the best coding practice, because it's just nice to have self. Does that answer your question? Okay, so there it is. So I'm going to set the input value. I'm going to set the input center. I actually never set radius up here, did I? Right, so maybe I should set the radius right here. We can actually do it with the same command right here. So filter set value. This is going to be the radius, and the value that we're sending in there is, I think, just radius. Is that right? Input radius. What's the problem here? Anybody know? Sending float to a parameter of incompatible type. It's expecting type ID. What's going on? Radius is a float. I need it to be type ID. How do I do that? Did you say blah? Block. No. I want to use an NS number. I want to encapsulate it, right? Hey, everything's happy. Good? Okay, let's just run this really, really quickly. So it should just have a center, or apply a distortion to every single incoming image, and it's going to do it essentially right in the center where we set it to go. Whoa. Wow. I've got a pinch distortion. Okay, but this whole thing was supposed to be based on updating filter parameters, right? So let's update the filter parameters. Okay, so I'm going to go in here to my main storyboard, and I want to get a gesture recognizer. How do I do that? Does anybody know? Hey, pan gesture recognizer. I'm just going to take that, I'm going to drag that out into this view. Wherever I place that, it's going to be looking for drag gestures and sending them back to the delegate. So I'm going to put it inside this view. So I've got a pan gesture recognizer in the entire view. Okay, so now if I go to my little assistant, Butler here, what I can do is I can just drag, control, drag. And this is going to be a UI pan gesture recognizer that I want to set in, and we'll say that user panned. Actually, we don't want to do that. We want to say panned from user with recognizer connect. All right. So let's go back here to my view controller. So is everybody okay with me connecting that UI pan gesture recognizer? Question.
Is there a way to make it only recognize motions on part of the screen?
Yeah. So the question is, can you make it just recognize on only part of the screen? Absolutely. If you had a smaller view and you only wanted that view to deal with the pan gesture recognition that happens inside of it, you can just do it inside that view, a container view or smaller view. Absolutely. And not only that, it would give you its pan location relative to that view. Right? So with my pan gesture recognizer, what do I have the ability to do? Well, first of all, let's get the point where the user is touching down, right? I want the location in view, right? So what that's going to do, I know it's going to return a CG point, right? So we'll just call it the point that it returns. All right, so I'm going to create that, and then I'm going to ask this sender, which is a UI pan gesture recognizer, for the location in the view. And the view that I'm going to send it is what? Self.view. Well, that's a really good option, and I can see why you guys said that. What I'm actually going to do is I'm going to go in here to my video manager, and I'm going to go dot video preview view, the view where my image is being displayed, and that's the view that I'm going to want it in.
So is that sitting on top of self?
So this view right here, this video preview view, is actually all the way in the back. It is all the way in the back, right? And that's something I set up for you in the video analgesic. So it actually creates that view, sets it all the way in the back right there for you to use, right? So I'm going to go ahead and get the coordinates that are inside of that view. The next thing that I'm going to do is I'm going to update self.center, right? So self.center, I'm going to say is equal to, I'm going to create a CI vector. And then let's do the same thing that we did here, vector with x and y. And the x that I'm going to get here is just point.x. And the y that I'm going to get here, because we're actually flipped, we're going to do point.y. And then I'm going to go to the edge of my preview view and subtract it back off, half of it. Okay? Well, plus the radius. So essentially what I'm going to do here is I'm going to say self, let's just copy it. So I'm going to say this view dot bounds, whoop, dot size dot the height. Not the way that the video analgesic is set up.
Wait, so x is height or width, right?
So the y right here is height inside of my video preview view.
But before it was width.
Yep. And that was because I was using self.view. So essentially what I've given you here is a view that is this and mirrored. Okay? And I'm exposing that here on purpose. That this is the way that it looks. Okay? Great, so this is going to work just fine. What's that? Yeah. Let's go ahead and subtract off the radius over 2. Right? And since we're flipped, the radius here, I think radius actually needs to exist a little somewhere else. All right, so float radius right here. I'm just going to declare this in my scope, class scope, right here. I could also make it a property. But essentially now everything's going to be happy. Okay, so I've got a pan gesture recognizer. It's going to output, and it's going to change the distortion on the screen. So let's go ahead and play. Okay, so we start in the middle, and I can drag it around. Hey, we can drag it onto my face. Oh, that's great. This is perfect, right? So I can drag it around. So I can, all of those filter parameters are being updated, which is great. Okay? Interesting. Nice. Okay, so we'll do that. And we'll just leave up this for the video. Be fine. Okay. That was Looking Live with distortion. Any questions on using the pinch filter distortion and how to set and kind of update parameters when you're outside of that processing block? Nope. Okay, good. Face detection. Okay? So face detection, the question that we're asking is a face in the picture and where is the face? We're not asking who is in the picture. We're just asking, is there a face? Okay? And there's some varying things that you might want to do for that, such as look at skin tones, try and find red eye, all of those different things that you might do with photography, and also some generic things if you're just wanting to follow someone around as their implementation is there. Wow, okay. The algorithm is not really given out. Apple doesn't really tell you what algorithm they're using. In almost all likelihood, they're using a variant of something called Viola-Jones, which is something we will talk about today. And it's most likely hardware accelerated, right? Which means that the parameters that they use, the features that they come back with to find these faces, they can spit them off to the hardware and have them run really, really, really quickly. They have some dedicated face detection hardware that is running. Okay? It's not completely automated. It's not completely on the hardware, but it probably is there. So very, very high level intuition before we dive into what this algorithm is. Essentially what this is the matching filter, right? So I have some kind of filter, which is a face. And I'm just going to kind of take it across the image and see wherever it matches. Like whenever I actually come across a face, it's going to have a really high value, right? And when I'm not on a face, it's going to have a low value, right? It's essentially this kind of linear filter that's coming across things as they go. All right, that is the model I want you to keep in your head as we go through some of the processing specifics of this. But this thing happens at multiple scales, right? I can't just like, I don't know how far away in an image someone's face. It could be of multiple sizes, right? So I could have this huge filter that I'm running across. I have a little face, right here. I'm coming across. It doesn't say that it registers, right? So it's a filter that has to happen at multiple scales from one another, different matching filters, right? Also, I don't know which orientation the image is going to be, right? So my matching filter has to kind of know the orientation of how I want to run my matching filter, and at what scales I want to run my matching filter. And if I want to detect faces that are at different scales, it's going to take a little more processing, a little more time, because I want to run those features bigger and smaller of my matching filter. Okay? All right. So now that you have the good idea of a matching filter, let's talk about what it's actually doing, because it's not really a matching filter. So face detection is done with what I'm going to call rectangle features. Rectangle features. Okay? And the features that it's using, those filters, those matching filters that it runs across the whole thing, look like this. Right? So essentially, I've got an image, which is right here. One of the features that I use is just two rectangles side by side. One of them is all ones right here and all zeros right here where it's black. Right? So the value of this feature, as I run it across the image, is just the sum of the pixels in the white area minus all of the pixels in the black area. So I take that and then I save it at the top left corner of where that feature, where that block is. Right? And I can do something right here. Here's another rectangle block where it's slightly different. Here's another rectangle block where I have a white, black, white. And then here's on the diagonal. Right? These are really, really simple features that I can run across an image. Right? Anybody know what the name of these features is called? Has anybody ever heard of wavelets? No? That's okay. These are called Haar wavelets. These are the simplest wavelets that you can have inside of an image. And they're used for tracking all sorts of objects, not just faces. Right? So generically, I'm going to talk about this for face detection. You can use this for detecting any kind of object that you want. So essentially, there are going to be some of these features right here that are better for faces than others. Okay? So this right here, this might not be a great feature for detecting faces, right? Like if I'm trying to subtract the left and the right side of the face together. However, this one might be. This might tell me where the nose is, if there's always a protrusion, kind of a dark spot that happens inside someone's face as I run this filter across. That might have a high value, right? So the best dark and light rectangles, those have already been chosen for you for face detection. Not only that, these features right here are really, really, really quick to calculate. Okay? Has anybody ever heard of a summed area table? No? Well, essentially, all I'm going to do is I'm going to start in the very top left at 0, 0 on the origin, and I'm going to start adding up the pixels, right? So if I'm right, if I essentially move this block right here, my summed area table, the value of this S at XY is going to be the value of all of the pixels inside of this square. Right? And that's, if I'm doing an image, that's really easy to create. Right? This is called an integral image. Right? So if my original image is here, my summed area table would look like this. I would start in the top left corner and just start taking a sum of all the rectangles. Right? So this value is 9 right here. Right? And that's because it's the value of all of these pixels in here. Can you guys see the mouse? It's okay? Right? So 4 plus 4 plus 1. Right? 16 is the value of this whole square right in here. Right? 17 is the value of this whole square right in here, the whole top. Right? Now the advantage of putting this summed area table together is that if I want to know the value of summing up the pixels inside any single rectangle inside this entire image, it's 4 operations, 4 additions. Right? So if I want to know the sum of this value S right here, well, I look at my summed area table and I take the value of C, which is the sum of this entire thing right here. I subtract off D, I subtract off B, and then I add back in A. Is everybody okay with that? On how that works? Those rectangles can be any size that I want. As long as I have done this integral image before, a very quick operation, I can get all of those Haar wavelet features any way that I want, just by 4 multiplies and additions. Very, very quick. Okay? And I can do it at multiple scales through the summed area table. It's a fast operation. Are you guys okay with this? All right, good. Okay. So now we've got our summed area table. We've got these features that we're looking at that we're going to do face detection with. The next thing we're going to do is train a bunch of classifiers with a lot of different examples, right? So the reason that these simple features work is because I've seen millions and millions of training examples before so that I can kind of fine-tune this algorithm so that those features work for face detection. So the way that it works is, let's say I have 4 different features here, C1, C2, C3, and C4, the same ones that I showed before, those rectangle features. I'm going to take my database here, and I'm going to say, okay, this C sub t classifier, I'm going to make that equal to 1 if its feature value is greater than some threshold. And the way that I get that threshold is by running that feature across all of these different faces that I have in my database. And when it's greater than some value, I say, hey, this is good. I'm going to say that is a face. Okay? And I'm going to run it on a bunch of images that don't have a face in it. And those are all negative examples. And I'm going to say, okay, I'm going to try and find the best threshold to say whether it is or is not a face from this one feature. And you can do that, and it won't work very well if you have one single feature, right? It won't work all that great if it's above that threshold. You're going to get a lot of false positives. It's not going to detect a whole lot of faces. But if you combine the outputs of all of these different features together, so if each of these become a classifier, then I can say, okay, my ensemble of classifiers that I have from all these different features, I'm going to say this is equal to 1. It is a face if this summation is greater than this summation. So essentially, I've got all of these C sub t values, which are all these different features that I have. And I'm going to multiply them by these different alpha values. So I'm going to say all of these different features multiplied by a bunch of different alphas. A single alpha per feature. And I'm going to say if that is greater than just the sum of the alpha values, then I'm going to say it is a face. It's an ensemble. And if it's not, I'm going to say it's not a face. These alpha values right here, what those weights are, that's the tricky part of this calculation. Does everybody see that? Now you really want to fine-tune those alpha values so that you can get a classifier that you want. This right here, this is machine learning 101. Finding those alpha values, that is what machine learning, data mining is all about. It's finding those optimal alpha values, right? You're going to set up essentially a minimization function, right? You want to minimize the error between the faces that you get out and these alpha values. As you adjust alpha, how does that affect how many faces you can get right and wrong, depending on your data set, your training labels?
Why is alpha?
Oh, this right here, why is the sum multiplied by 1/2? Because essentially these C sub t values, whenever I take alpha, so let's say these C sub t values were all equal to 1. They all said that it was a face. Then essentially, like that would essentially be the sum of all the alpha values, right? So if at least half of these are saying it is a face, then I'm going to say, okay, the whole thing is a face. Is that okay? But that's not actually, it doesn't stop there. Each of these ensemble classifiers, you can create a bunch of different ones. And you can cascade them all together. And you can combine them using an algorithm called AdaBoost. And then, if you're a computer scientist, you're going to come along and you're going to say, why are you using AdaBoost? I'm going to use a support vector machine, even though I don't know what it does. And you're going to do better than anybody has ever done. You're going to publish a paper on it. And everybody's going to know your name. And it's going to be Viola Jones. All right? So, essentially, this is a very high-level view of what these classifiers are doing in the background. Okay, so learning. It's really tough to train a Viola Jones face detection, right? You're going to need examples in a lot of different lighting conditions with different colors of illuminations, different sources. You're going to need different poses of the face as you move, or if I do this, of people and images. You're going to need people of different genders, races, at a whole bunch of different scales. Face detection was really, really hard. Does anybody know what made it 1,000 times better? More data when everyone started posting pictures to Facebook and highlighted themselves in squares. It gave the face detection community billions of face examples overnight. All right? So now they took all of these classifiers and they were like, let's really find out which one's the best. And they found it. And Apple did the same thing. Once your algorithm is trained, once this Viola Jones face detection is trained, it's really, really fast to use, right? All you have to do is get that integral image. You take that sum across the image this way. You get the relevant features, right? So we've got all this huge training data from Facebook, right? So there's a bunch of different features that we know we need to run on the image, which are just rectangles. Those rectangles that we talked about. And then I'm going to multiply them with a bunch of weights that I've already learned. All those alpha values are already done. It's done for you. That is how the iOS implementation happens. All of those weights, all of those values are found already for you at a bunch of different poses with a bunch of different people at a lot of different illuminations. All of that is done. So how do you use it? Let's do it. I need to speed up a little. Okay, face detection in iOS. It's going to be a really, really similar pipeline to applying a filter to an image. Essentially what we're going to use here is an instance of the CI detector class. And we're going to specify where the processing should occur. Where's the processing going to occur if I didn't beat that over your head last time? Not on the main queue, okay? Where should it occur if I'm doing video processing? Context of the GPU. All right, now everyone's like, oh, yeah, he said that a lot last time. Okay, so essentially, here's what we're going to do. I'm going to create an NS dictionary of options, and I'm going to say, okay, so here's the optionary for a key CI detector accuracy. The CI detector accuracy, low. I can also do high. Anybody guess what the difference might be? Yeah. How accurate it is at determining a face. Why would I choose low right here?
Faster.
It's faster. It's a lot faster. And we're doing video. Right? You can do really high accuracy, but maybe you only want to do that if you're doing this on an image that you're doing some processing on. We're going to be doing it on video, so maybe I want that accuracy is low. The next thing I'm going to do is create an instance of the CI detector class. So my CI detector equals CI detector, detector of type, CI detector type face. The context where I want it to do all the processing, I'm actually going to say is my video manager. And all I'm going to do is grab a handle to my CI context, which is set up for you with video analgesic. So I'm just going to give it that context, and then I'm going to give it the options right here that I had. Right? Only faces currently can be detected using the CI detector class. Okay? That is probably going to change with iOS 8 or 9 or something. They're going to enable a lot of different detectors. But right now, the only thing you can put in right here is CI detector type face. I'm going to give it the context and the options. So now, I can run my detector on some image and give it some options. So I'm going to say, okay, so here's detector, features in image, my camera image, and I'm going to get an NS array of features. Okay? All of those features are faces that it's already found. So for CI face feature F in features, I can just print out the rectangle of where those faces are in the image. Super easy. So where would I do this? Inside of a block. So here are the options that I'm putting in there. The options are the CI detector image orientation, and I'm just going to call this function on video analgesic, which is CI orientation from device orientation. And then I'm going to actually just give the status bar orientation and send that in. Right? The reason this line of code right here, I just saved you weeks. Okay? You were going to get frustrated and start pulling your hair out because you're running the face detector and you don't know exactly which orientation you're in. Just grab it from the video analgesic, okay? And you're going to tell it which orientation you're in. Okay? So, let's do it. Through the looking glass. Let's do some face detection. Okay, let's get rid of all this noise. Oh, not that. That's the one thing that threw us up last time. Yeah, we'll leave the radius in. We'll go ahead and start it from there. That's fine. So we have this pinch distortion. Okay, the next thing that we're going to want to do here is create some options, right? For CI detect. If I want to do face detection on the camera image that's coming in. Yeah? Okay, good. All right. Actually, let's just do an NS dictionary. And we will call it options. And it's going to be equal to basically everything that we saw before. I'm going to have CI, detector accuracy. And then I'm going to do what? CI detector accuracy low. Low. We can do it high too if you want. We'll try it low. There is not a medium. There is not. Okay, so it's giving me a warning that it's not being used right now. The next thing we want to do is create a detector class, right? So back up here, our detector. Okay, so I'll create CI detector. And we'll call this class function CI detector. Like this. And then all I'm going to do here is get a detector of type CI face, right? Detector of type. The only thing that's supported is CI detector type face. The context that I'm going to use is my self, dot video manager dot CI context. And the options that I'm going to give it are the options that I just created. Okay? Good. Now what? Yep, so let's go in here. Let's detect some faces inside of the video manager block. Okay? So, first thing I'm going to do is let's create some options right here. Let's say options are equal to, this is all I'm going to do right here is set up the orientation. So this is CI detector image orientation. And what I'm going to pass in here is this handy dandy function where I've got self dot video manager. This is CI, whoops, what did I call it? CI orientation. What? Oh, you know what? I don't know why it's not letting me. Well, it's fine. CI orientation from device orientation like this. Wow, it is having a lot of trouble with this. Oh. It's never Xcode's problem when IntelliSense isn't working. It's usually your own. Anyway. So what I'm going to put in here is I'm just going to get a handle to the UI application. So UI application like this. And then let's get a handle to the shared application. And I'm going to say the status bar orientation. And send that in. All right. That should be fine. Why doesn't it like that? Oh, because I'm changing options. So we'll make options a block right there. Good. Detector is still not being used, but we can create an ins array here. All right, so ins array, say f is equal to my detector features in image, and then the image that I'm going to give it is my camera. It's my camera image, like this. Voila. Except I need a pointer. Okay, so there's for features in the image, camera image, f. Now what do I want to do? I want to display. Let's take this distortion effect and put it right smack dab in the middle of anyone's face. Okay? Okay. So for CI face feature F, sorry, we'll call this, let's just call this face features, and we'll call this face in face features, like that. But now what we want to do here is what? Instead of sending this weak self.center, what I actually want to do here is send in the bounds that are from each face right here and use that as my x and my y, right? So let's do this. Let's say float x is equal to f face dot bounds. I get the bounds that are around each face from these features. I'm going to say, give me the origin of that. Right, but I want to put it in the middle of the face, right? So I'm going to say f dot bounds dot what? Height divided by 2. Okay. Yes, it is. Why is f even working? Oh, it's not. Okay. Okay, and we'll say the same thing right here. Right, except, well, so x and y would be nice. But then instead of, we'll do a width. Size. There. Jeez. Okay, now I can create a CI vector. Sure. And we will say vect right here, and it's going to be equal to a CI vector. This should be getting familiar now. Vector with x and y. Right here. And we'll put in xx and yy, unless I've totally reversed x and y. And then this vector is what I want to use right here for my center. Right, so I get the face bounds, the very middle of it, put it right here, and call it good. Right, so I'm still updating the input center. And this is going to work for every single face that I see inside this image, right? Okay. Unused variable weak self. Perfect. And I can move around.
Oh my gosh.
Nice. I can move a little closer, back farther away, and closer. Wow, it's actually doing a lot better than I thought it would. This is great. Wonderful. We could use this from now on inside the class.
Oh, the copy.
Right? But see, I can put my hand up here. It's fine.
That's a really good detection.
It's actually very good. And this is detector low. Okay? How fast is this thing running? It's using 110% of my CPU.
Wait, what?
Essentially, we could reduce the frame rate. I'm running at like 30 frames a second right now. Probably not I mean, it's doing a lot of detection 30 times a second and a lot of filtering too. Okay?
I mean, that's not supposed to be possible, right?
What, to use 111%? I think it's because it's based off of the application. And like, here's how much you should be using. Here's how much you are using.
Oh, okay.
Does that make sense?
So it's not actually using 112%.
It's not using 112%. I think I've actually gotten this up to 193% before. Yeah. Okay. Perfect. So you show your friends. Okay. Let's just keep it up there. Why not? Let's not, because it's going to keep going back and forth. And like it's going to be really distracting. Okay. Oh, that's better. That's much better. Excellent. Okay. Questions on face detection? That was through the looking glass. You can do any kind of distortion that you want right there. It's really, really fun. A window? Yes, you can, but you're going to need to do some graphics if you want to do that. I would recommend applying filters to it. Like you can actually do compositing filters, right? So if I have like I could create an image with a based on my where the face occurs, I can create an image which is black everywhere except it's got a big green circle wherever there's a face or wherever there's two eyes. And then I can call a CI compositing filter and combine those two images, right? So anywhere it's not black, will be the face. And then you can just have these two kind of things over the eyes or the mouth or something like that. Or maybe you could only do something when someone's smiling. So essentially, there's many tracking mechanisms that are supported for this. There's a lot of different variables that you can throw in there. Check out the CI detector API, get on Apple and take a look at it. Because when you want eye and mouth location, it's pretty easy to do. Okay? Instead of face.bounds, you can imagine it'll be something very, very similar. Okay? To get faces. Smile detection is there. You can absolutely do it. It's built into the API. That's new with iOS 7. And then blinking and winking. So if I can do the left eye and the right eye, it will detect them separately which ones are closed.
Does that automatically?
It does not do that automatically. You'll have to set that up, but it is worth extra credit.
Oh, that one's not built in.
It's not, well, yes it is. It is built in, but I want you to use the API to figure out how to use it.
Yeah.
If you got questions about it, you just run into problems, you can come see me. But it's not too bad to use. Okay? Questions?
So does the Apple provide orientation on the face view?
They do not. So one of the options that we put in for the face detection was the image orientation. For speed, it's only going to run it in that orientation. If I want to do multiple orientations, I need to run separate detectors with different orientation filters. Does that make sense? So I need to run it in landscape mode and run it in portrait mode. I could run it in left and right landscape mode, but that would be a complete waste of time. Okay? So all of the eye location, the mouth tracking, everything that's there is essentially using a variant of that Haar wavelet method that we talked about before, the Viola-Jones. All that is generic tracking. So we can figure out where the eyes and the mouth are. Okay. So module A right here, where you have to create and do mouth position, you are ready to go on that. You guys agree? Okay, good. Computer vision. Face detection really just is the beginning. As I mentioned before, you can do tracking of any object with that method. If you wanted to track something else using the method that we just talked about, what would you need? Let's say I wanted to detect this hand motion around an image. What would I need? A bunch of different examples of what this looks like, right? It's not the method that's expensive. It's getting all of the training data, and cleaning the training data and getting it properly, and then kind of sending it off to all of these different kind of training algorithms that you have. And not only that, if you want to do it in iOS, you're kind of out of luck, right? They've trained up this face detection algorithm, and they haven't trained up any other detectors for you. So if you wanted to use this method, you'd have to do it on your own. So you can, and we'll talk about how to do that. You could also do recognition, right? So I wanted to know who this was, or maybe you want to do gender recognition. This is a man versus a woman that's there, or a child, when some of the facial feature detection hasn't really built in yet. If you wanted to do that, there's something called eigenfaces or Fisher faces, which if you were in linear algebra and you said eigenvectors, when am I ever going to use that? Here's where it is. Here's where you use it. Don't try to do that on your own because it takes a little while and you'd have to get a lot of implementation and corrective kind of methods out there to train up your own classifier. But it's straightforward to do. But computer vision, you can do more than just tracking. Any kind of knowledge that we can gather from some type of streaming video input, such as finding edges, finding lines and shapes that are inside of an image, and looking at the different color spaces that exist, all that would be considered part of computer vision. And so we're just extracting knowledge from a scene. And so I want to give you the tools to be able to do a lot of these different operations. So that is computer vision. So computer vision in iOS, well, the mobile camera, I would say the mobile camera is a pretty rich medium for doing a lot of different types. So why would you ever want to do computer vision on a mobile device? Well, if you're doing enhancement on images, right? So this type of thing right here, this is a Facetune app where they're actually going in and they're detecting everywhere where the face occurs and applying some Gaussian filters into it, which is essentially for smoothing on the face, right? So that would be an enhancement algorithm. You can go in and look at increasing the skin tones and reducing glare, right? Interaction and augmented reality. So this is an application that you can download here where essentially you see all of these people just sitting around and they're all pointing their devices towards the ottoman that's right here in the middle. The ottoman has like a little square on it with a bunch of different circles, right? And so essentially what's happening in real time is it's transposing augmented reality. Like it's taking some graphics and it's actually putting the tower on the ottoman. And you can kind of move around in the game, right? So tracking would be, this is a rich medium for gaming if you wanted to do this. I've seen applications where you can hold up, let's say, the iPad and you want to like shoot a ball. And so essentially it creates this hoop. Like you hold up, you take an image, and it creates a hoop. And it will place that on the wall in the exact same place. So you can move this around, and you're just moving around where the hoop is, and then you throw the ball into it. Right? So augmented reality, certainly one of those things. Gaming is probably the most lucrative part of it, but you can imagine using this for assistive applications, right? Finding a bus stop, seeing if it's your number, right? If you're blind, and getting on the thing. And that's where a lot of this comes into use for assistive technologies. But also one of the places where you can use computer vision a lot is in health, right? Oh, and play with your whole body. Yeah, so it's kind of a whatever. It's fine. So health. All right, so one of the applications that you can download from the App Store is Azumio's little instant heart rate monitor, which we are going to recreate in this class. It's Module B. It doesn't have to be as good as theirs. It doesn't have to be FDA approved. Neither is theirs, by the way. Huh? No. There's very few applications that are FDA approved. So, health monitoring. Detecting heart rate from the camera is probably the most common application. It's one of the easiest things to do. It's something that we can do in one lab, so we're going to go ahead and do it. What is the function of the heart? If we want to detect the heart rate from the camera, there's a couple of things we need to know about the physiology of the heart before we can actually create an algorithm to go in and find out. We need to know what we're sensing and why things are changing in someone's finger when they place it over the camera, right? And that way we have a better idea of what the mechanism of action is behind what we're trying to sense here. So essentially the function of the heart. Base level, you're going to pump oxygenated blood from the lungs to the rest of the body. That is what the heart does, right? And bring back the deoxygenated blood so that it can transfuse, go along the lungs, and essentially kind of diffuse oxygen into the blood so that it can resupply the rest of the body, right? Breathe in, breathe out. So it's completely related to pulmonary. Okay? That is the base level. There's other things the heart does, obviously, but you're not going to survive without it doing this. So at its heart, at its center, the heart is just a pump. Okay? And it maintains pressure and it maintains flow rate throughout the body, right? It is just a really, really well-engineered pump. So no pump that you can buy works continuously. It's a series of pressure buildups, release, buildup, release, right? So if you bought a pump that you're going to pump water with, it's essentially a huge turbine which is building up pressure of water and then pumping it out, building up pressure of water and then pumping it out, right? And so if you were to look at the pressure, let's say just in your plumbing line, right? It's actually going like this. It's going in and out. It's just like the pressure that builds up in the veins of the body. And that cycle is the heartbeat. So here's a picture of the human heart. A cartoonish picture. I didn't want anybody to pass out. But essentially, you've got two different inputs to the heart and a lot of different outputs. Essentially, you have the vena cava right here, which is going to take deoxygenated blood, and that enters through the vena cava. I'm sorry, we're actually talking about physiology, but this is computer science. You should be used to it. You use computer science in the real world, okay? So essentially, you're going to use it in a bunch of different applications, right? So essentially, blood comes into the heart through the vena cava and through this part of the aorta where it enters the left atrium right here. And when the heart beats, the first thing that happens is the aortic valve, which is right here, and the valve of the vena cava open, and it allows blood to flow into the heart. After that, blood enters so it goes from the atrium right here into the ventricles of the heart, and it holds the blood there. So it can't go back out into the body. It holds it right there. This whole process where blood enters the vena cava and the aortic valve and then sits inside the ventricles takes about 1/10 of a second. All right, so 1/10 of a second occurs right here. And then you've got blood that's inside each of these ventricles. Then the heart does its little dub-dub, and it pumps and ejects those out through the aorta, right? And then out through the outgoing vena cava, right? So it pumps blood to the rest of the heart and to the lungs. That action right there, where the heart is actually just pulling itself in, that takes about 1/4 second. After that, the heart relaxes and it lets blood back into itself, and that takes about a full 1/2 second, right? So this whole thing right here is one heartbeat, where you have the valves open, a pump, and then the heart relaxes for about 1/2 second so the blood can re-enter through the heart. Okay. So because it's this pump, the pressure in the body, the pressure that's in the veins changes. So if we were to look at the blood pressure over time during this process, what we would see is that the pressure is low, it rises up when the heart is pumping, and then as the heart relaxes, we get this slow fall off right here, okay? And this happens, well, right here, this is happening more than 1 time per second, right? Slightly more than 1 time per second, right? So as the heartbeat, if we were to look at the heartbeat over time and we were to look at the blood pressure inside of the veins, it would be doing this. It's kind of this oscillating thing going up and down like this, right? Where we get this sharp increase right here, and then a slow decrease. Sharp increase, slow decrease. I'm going over this in painstaking detail because you guys are going to be looking for this signal on the phone. So what's happening right here is underneath the skin, the capillaries are expanding and shrinking back in, right? As the blood pressure goes like this, you've got your veins in your body, right? And those are not hard veins. They can move around a little bit. They can do this. They can kind of squish around, right? So when the heart pumps, they do this really quickly and then come back down as the pressure goes down. And they do this, right? What does that mean? Well, that means that more blood is underneath the skin when the capillaries expand. You get more blood. So that means there's going to be a shift in the redness of the finger from oxygenated blood. There's going to be a shift in the blueness of the finger from deoxygenated blood. Right? Has anybody ever seen deoxygenated blood? It's blue. It's bright blue. Okay? Oxygenated blood is bright red. I mean, essentially, when you're doing this, there's more molecules that are underneath the skin. So if you're shining a light under there, you've seen it, it looks red, right, when you look at it on top of the fingernail. Essentially, there are more molecules for that light to bounce off of, and we can detect from the camera. So if you hold the finger over the camera and you light the torch right here, what you're going to see is this is actually a video that I'm playing right here, and it's not even going to, oh, come on, it looks black up there, really? Okay, so I made a video of what it looks like when the camera is there, and from my screen it looks really, really great. You can actually see it shift a little bit. So it goes like this. So you can see kind of a, and then it's real slow, real slow. If you look at the video of this, I just wanted to prove to you that it does exist. If I were to take that signal, right, that redness signal over time, and take a look at it, that is what would be called the PPG signal, photoplethysmography. All right? It's just the variation in redness, variation in color, not necessarily redness, variation in color as the heart beats. Okay? You can measure that in a lot of different places on the body. The finger is one place to do it. You can also do it on the earlobe. Okay? Any place where you can expect that there's a lot of movement in the capillaries, where you have a lot of different blood endings underneath the skin. Okay? Caveats. There are some caveats to this method. Don't press too hard on the camera. Why would that be a caveat? I can't hear anything. What does it say? It'll affect the blood in your finger. How? It'll stop the blood flow in the finger. If you press it too hard, I've had people that are pressing really hard. It's like, it's not detecting my heartbeat. That's because you've cut off blood flow to your finger. Okay? And seriously, and it doesn't take much. This is a very fleshy part of the body, right? You can very easily cut off the blood with the finger. Vasoconstriction and vasodilation. If you are a smoker, that causes your veins to constrict up a little bit more than other people. There's not as much blood flowing in your fingers. It's going to be harder to detect. Okay? But if you drink alcohol, vasodilation, that actually expands the capillaries and it makes them easier to expand. I am not telling you for this lab to drink. That is not what I'm doing. But it's a good example because it got everybody's attention. All right? So what I'm trying to say is there's different physiologies, right? If you have really cold hands, you probably don't have the greatest circulation. Okay? That's going to affect the signal that you're seeing. Okay? Find someone that has warm hands and have them be your tester for this. Okay? Bigger surface areas are better, right? More light to bounce off of. What does that mean? A little more accurate. Maybe you want to use the thumb versus the index finger. Index finger will probably work, almost certainly. The thumb might be a little bit better. Okay? Don't move around too much. Why would that be a factor? Yeah, if you're sitting there moving your finger around a little bit or just kind of your body, you're trying to do this, you're moving across the camera, you're changing the intensity of the signal. The signal that we're trying to extract is pretty small anyway, so movement really starts to shift the intensity of the redness, especially if it causes you to have a different pressure against the camera. Okay, so it's not a perfect method to get heart rate. Also, the heart is not the only organ that increases the pressure in the veins. What else might increase the pressure in, say, the capillaries, right? You increase pressure, you get more redness and things. Anybody know? Exercising will do it, but is there an organ that is kind of periodically increasing the pressure and decreasing the pressure in the body? The lungs. That's the biggest one. Actually, from the PPG signal, if you really get good at sensing it, you'll see a modulation of that from people breathing. So you could, if you wanted to, look at the way that goes over time, and you could get breathing rate as well, just from the finger. It's a lot tougher. I'm not asking you to detect that. Okay. So what method might you use to measure the PPG signal from the camera? Anybody have any ideas? What would you do? What was the first thing that you would try? Oh, you guys are tough today. You're like, the core motion assignment's due in like 4 minutes. You could turn it into a grayscale image. You could do that. You could look at the redness channel, right? If you're just looking at it over time, let's say I take the redness channel at 30 frames a second, and I take the average redness in the whole image. I just plotted it over time. That might work. Grayscale would probably also work, right? Because you're getting changes in a lot of different illumination and intensity. Okay? So that's great. Once you have the signal, that's there. But I want the beats per minute. How are you going to make me happy? Once you have that signal. Count the beats. Yeah. How might you do that? This is like pulling teeth. You could do the FFT. You could look at the FFT over time. It's a little bit harder. I wouldn't recommend using the FFT on this one because the signal's really, really small. There's a lot of preparation work you need to do to the signal to get the FFT to work. You can do it. It's tougher. But if you just count, look for local maxima. Oh, everybody's like, what? You could look for local maxima over different durations and count how many times you get a maxima in, say, 5 seconds. And give me the beats per minute, an estimate. That would work. How might you get access to all of those pixels? We've got 2 minutes left. We'll save this for next time, where we will talk about OpenCV in iOS. Essentially, the introduction for that is it's the Open Computer Vision Library. It's something that was created and released by Intel. And it's got a lot of common functions that people are interested in just doing pixel-wise operations with. It is written in C++, but it has many, many different wrappers. So for instance, there's an MGU, which is a .NET wrapper. So you could use that in C#, Visual C++. There's a Python wrapper. There's a Java wrapper, which you can use this for Android. There's lots and lots of different wrappers. But essentially, this is a C++ library. There are some hardware accelerations on iOS. There is not as many hardware accelerations that use the GPU. It's not going to be as fast as Core Image. It's still going to be really fast. Okay? It uses the Accelerate framework wherever it can. But that's not a whole lot of places. Okay? It can't do things on the GPU. So expect a slightly slower processing. You might use 30%, where in Core Image you might use 10% of the CPU. It's still fast. All right. We will save that for next time.